record on this computer. Welcome back to lecture 7. So previously we saw that the maximal function, the Hardy Littlewood maximal function over balls, was bounded on L1 to weak L1. It satisfied this weak 1-1 inequality. And we also saw that it's bounded on L infinity. Of course, there's a whole bunch of P between 1 and infinity. And it turns out that knowing these two extremes is enough to get everything in between. And that's handled by this following proposition. So it's going to be a bit more abstract. Just start with a measure space. That's X, and the measure is mu, and a sublinear operator T. Assume that it's weak type 1-1, which means it satisfied that inequality. Oops. That is T F is greater than alpha is less than or equal to some constant, alpha inverse times F in L1. That constant is depending on the operator, but not on the function. And then strong type infinity, which is just that T of F is less than or equal to, let's call that constant 1, and this constant C infinity times the L infinity norm of F. And then our claim is that T is strong type PP, meaning that there exists a constant CP depending on P, such that TF in LP is at most CP F in LP. And this is LP spaces with respect to X and a measure mu. And the theorem, this proposition actually also says, a real interpolation says that we can bound this CP in terms of the other constants C1 and C infinity that we had before. Right. Maybe also to remind you, what is a sublinear operator? Well, it's an operator on functions, and it satisfies the triangle inequality, TF plus G is less than or equal to T of F plus T of G, absolute value. And T of CF was C of TF. Right, so it's not quite linear operator like each of the averages was, but it's sublinear, meaning it's not going to be bigger than the linear combination. And the maximal function is exactly an example of this, of a sublinear operator. Oh, which I say right here. And this I'm defining these on, there's some space of functions which I'm not being too precise about, for which the action of T is well defined. For our purposes, remember we said that all smooth, compactly supported functions, we could define the maximal function for, and all of those lie in each LP space. So that's a perfectly good thing to use here. Now, the interpolation proposition is another example of our low and high decompositions. Before, when we were doing the circle method, we had that we had something of the following. We had that the delta function on ZD at the origin was roughly, meaning up to some error terms that we had to do a bit of work to get, the delta function in the 2-adics in d-dimensional space times the delta function in the 3-adics, and so on, and times the delta function in RD. The modern viewpoint of this is that the major arcs, the major arc decomposition we had, is analogous to low frequencies in Fourier analysis, and the minor arcs are analogous to high frequencies. But then also on the major arcs, you have another sort of low and high component, which is corresponding to what's happening in the real place. Here, we're not dealing with frequencies anymore. We're actually dealing with just low and high parts of the function in a spatial sense. Okay. And how is that done? Well, it's typically, these are described as good and bad parts of the function because of the connection to Calder and Zygmunt theory. So what is that? We pick some altitude alpha. That's our height, which we cut our function into two pieces. So suppose I have a continuous function and one variable again. Maybe should have drawn something with more variation. I pick my altitude alpha. I slice things at. And then I cut my function into two pieces. Well, it's actually a bunch of pieces by the intervals, but it's two parts by how we'll use it. So when f has height at most than alpha, that'll be the low part, because it's bounded above by something that we're going to control later on or optimize later on. And then that's our good part, G. Our bad part, or the high part, is when it's all bigger than alpha. And we don't have much control on that. We just know it's bigger than that. But it could be a lot bigger than it. Who knows? So the good part, aka the low part, well, we introduced an L infinity cutoff by saying just picking out the part that was always bounded by alpha, right? Well, that suggests that since our function, since our operator, I mean, is bounded on L infinity, we should try and just write out what this means. Well, when we do that, when we apply t to the good part, we find out that it's exactly just this inequality. Right? The good part's bounded by alpha. So when I look at the L infinity norm of the operator applied to the good part, it's the most C infinity times alpha. Not too deep there. This does have the knock-on effect, though. That's, yeah, this has a knock-on effect we'll get to in a minute. We got to see how to use this. Let's go to the bad part, or the high part. Again, in a physical sense, not a frequency sense. We cut off, our altitude cut off the good part, all the low parts, and then we're left with the high part. And that's definitely not an L infinity. What it is it's primed for weak L1, because it's this tall, spiky behavior, remember? And so if we have it, if we have a function in LP, it turns out this bad part, the high part, is in L1. And we have this bound for the L infinity, the weak L1 norm. So what is this bound is another way of writing the statement that, so this thing is what I mean. I meant the following. Part of TB greater than alpha in measure is at most C1 alpha inverse times the L1 norm of B. Now, it's not immediately obvious why if F is an LP, B is an L1. Let's see why that's the case. I started with some function. I've forgotten why this is true.
Kevin, I think you can just bound the absolute value of f by the absolute value, or the absolute value of b by the absolute value of b to the p times some value depending on alpha.
Yes, it's the
That's all you have to do.
It's the layer cake decomposition, right?
No, you don't even need a layer cake decomposition.
So you're just saying,
I'm just saying, like, you're in a situation where b is larger than some number alpha. So b to the p.
Oh, right, is greater than alpha to the p minus 1, the integral of b. Thank you. Yeah, it's very simple, isn't it? Sorry, I went, yeah, totally escaped me for a moment there. Great, thank you, Rob. Yes, you just use this inequality. Like you said, b is greater than alpha. So we have that, and we know that this thing is finite. Voila. Great. Now let's combine these two things and see how they interact. I take my function, f is equal to a low part plus a high part, or a good part plus a bad part. And by sublinearity, I know that means that t of f is at most t of g plus t of b, pointwise. Now, the good part we said was bounded in L infinity. So I actually know that this is always less than or equal to C infinity alpha. That implies that when I look at a slightly bigger level, I get the following containment, right? If I look at T of F in 2 times C infinity alpha, that's contained in the where T of B is bigger than C infinity of alpha, because this cancels out one of those just by the triangle inequality. And now we can use Chebyshev's inequality, or maybe it's Chebyshev-Markov. What is that? It's just, it tells us, oh, it uses the vertical layer cake decomposition of the LP norm of a function. So I can write the LP norm to the pth power actually as this vertical layer cake decomposition. Let's just take that for granted from real analysis. It's a version of Fubini's theorem. And well, we can replace it by squeezing in a factor of 2 C infinity. Because if I look at d alpha over alpha, or I should say alpha lambda. Okay, I look at d alpha over alpha, and then I squeeze in a factor of lambda to dilate it by, right? Well, that is just equal to it for any positive alpha. So it doesn't change this measure at all. However, it does affect this alpha to the p, and that's where we get this factor coming from. But we saw this containment from before. So we enlarge our set, or the measure of our set, by considering this, by replacing when t of f is greater than 2c infinity alpha by t of b. And we just need to handle the last integral now. That's pretty easy too. We are going to use this this exact inequality that we wrote down a moment ago that Rob was saying. Great. I peel off one factor of alpha, group it with the measure, and this happens to be bounded by the L1 norm of B because of the boundedness, weak 1-1 boundedness. And all I've lost is a factor of C1, but I've picked up a power of alpha, or I've overcome that. And then this just gives you the following integral by, again, the vertical layer cake decomposition, or Fubini's theorem. And that was because B was just defined as F times where F is bigger than alpha. No, we haven't done much now other than plug in definitions. And great, so Fubini's theorem saves the day. This actually gives us a way to express the P norm of our function. And then altogether, we obtain exactly the bound that we thought, or that we wanted, but to the pth power. So when I take 1 over pth roots, we get the 2 and the C infinity 1 minus 1 over p, and then C1 to the 1 over p as the as we wanted in the proposition. Great. Are there any questions or corrections at the moment? It's a nice argument. We see that just splitting our function at each altitude into these low and high parts, we could get a different bound for each piece using the two different bits of information we had: weak 1 boundedness and L infinity boundedness. And that for those are useful in the low and high parts respectively. Nope, sorry. Yes, high and low parts respectively. And then the rest was just basically Fubini's theorem and vertical layer cake. It's just understanding how these level sets decompose our function, or the profile of our function. So let's get on to some applications and why people outside of harmonic analysis might be interested in this. So first off, if you go back and read Hardy Littlewood's paper on the matter, they have a bit of difficulty motivating their maximal function, which I think is actually a discrete version of ours. And I mean, they try and sweep it under the rug by basically saying, oh, here's a cool analogy with crickets, which Hardy was obsessed with, but was otherwise irrelevant to the theorem. And they say in the paper that, we expect this to be an important thing, which anyone could write that in a paper, but it turned out that it's really actually turned out to be an incredibly fundamental aspect of modern harmonic analysis. And sort of applications came later. I tried to say, we're doing this weird process. I don't have any motivation for it. And it's because the motivation came afterwards. And let's get to what some of those things were. So it turns out you can imply the Lebesgue differentiation theorem, which was known beforehand, but this proof came about afterwards. And it's also telling you that LP classes are really the right space to work with in a lot of problems. And there's also, sort of in the opposite regime of that, the Birkhoff pointwise ergodic theorem, which says if you start with a measure preserving operator on some probability space, so my probability space is a space X, it's got a class of measurable subsets that satisfy the usual properties, and a measure mu, and then this T being a measure preserving operator, if we recall from lecture 1, is if E is one of these measurable sets, and I look at T inverse of E, the measure of that is equal to the measure of E. If you look at that, that gives you a measure preserving system. And if you also assume that T is ergodic, then you have the following pointwise ergodic theorem. For any function in L1 on your measure space, your probability space, the time averages tend to the space average as time goes to infinity. On the face of it, I think it's kind of hard to see how the averages, the Hardy Littlewood maximal function comes into play here. For the Lebesgue differentiation theorem, it's not too hard to see. You want to control what's happening to nearby values of f, right? But this is a function on Rd, and the Hardy Littlewood Maxwell theorem was about functions on Rd. This is not about functions on Rd, it's about functions on some abstract measure preserving system. All right, I'll leave the Lebesgue differentiation theorem to the notes. However, what I really want to do in the rest of this lecture is prove Birkhoff's ergodic theorem. So it's not the same maximal function that we've already considered. The maximal function we did was this continuous one over R and RD or Rn. This one now is actually, the averages are on a measure preserving system, right? Each one of these averages is sort of a right-handed average. It's going to the right. So as I look along the orbit applied to a point, I'm sampling along that orbit. I'm going forward in the future. Whereas the Hardy Littlewood maximal function was looking at things in RD, and then it was saying, I'm looking at all intervals centered at a point. Now I'm going in one direction, and I'm sampling to average that way. You can still define, those are perfectly valid averages, and you can define a valid maximal function. And it turns out that this is weak type 1, strong type PP for all P between 1 and infinity. As before, you can see the L infinity boundedness quite readily. If my function on now some abstract space is always bounded by 10, each of these averages is always bounded by 10, and hence the maximal function is always bounded by 10. The weak 1 boundedness is not so easy to see. We don't have this. Why would our space have any sort of ball structure to begin with? We haven't assumed anything like that. It turns out that there is some latent ball structure coming from the integers. And that actually brings us to a discrete Hardy Littlewood maximal function. So this is really a sort of another great insight, was that any of these ergodic averages, all of these ergodic averages are really a manifestation or different instances of a single discrete Hardy Littlewood maximal function. That maximal function is defined on the integers now, and this is where the right-handedness comes in. If I look at some integer x, I'm going to average over the next n integer, the average of the function at the values of the next n integers. So I'm looking at the values just to the right of it. I'm not even looking at the point itself, just the ones to the right of it. And great, you have perfectly well-defined averages. You can define the maximal function as before. It's the supremum over all the possible averages in absolute value. And it turns out this is, again, weak type 1 and strong type PP. I will not prove this discrete Hardy Littlewood maximal function. It is a variant of the argument that we gave for the balls. And actually that ball, that ball argument, the Vitali covering lemma, is incredibly general. What we really need is that is some statement about how intervals expanded overlap with each other. And I think it's a very good exercise to see how to do it when you've given yourself an orientation suddenly. Great. But I will prove how I will prove two steps into proving the Birkhoff pointwise ergodic theorem. One, that this ergodic maximal function implies pointwise convergence. And two, how this discrete Hardy Littlewood maximal function implies the weak 1 or strong type PP bound for that implies a corresponding one for the ergodic maximal function. And then that's where we'll stop. So again, this is the main motivation in the rest of this lecture is to give a proof of the Birkhoff pointwise ergodic theorem, which said, just to remind you, because it's been a little bit, that these time averages converge to the space average almost everywhere. It didn't highlight that fact before, but it's almost everywhere with respect to that measure on the measure preserving system. A very good example to keep in mind here is if your measure preserving system is translation on the torus, so on R mod Z, translation by alpha in R mod Z. This is it's a measure preserving system for any alpha. Alpha could be 0, it could be a half, it can be pi mod 1, whatever. And you form this, so you take a point and then you're looking at f of x n plus alpha as your orbit. And it's ergodic precisely when alpha is irrational. It is not ergodic when alpha is rational. And those are things I'll leave to the reader and the notes. But this is a very good example to think of because we know that when you have an irrational rotation that it equidistributes on the torus, and ergodicity is keeping the idea that these time averages are really filling out the whole space because it converges to the space average. Fantastic. Let's prove how the pointwise convergence follows from the ergodic maximal function. There's a couple of twists here, a couple of interesting facets. LP spaces on a finite measure space are nested. So unlike RD, each LP space, if I take an LP and an LQ for P not equal to Qs, there's a function in one that's not in the other, and vice versa. But if I do a finite measure space, suddenly, as I increase the P in an LP class, that decreases the space. So I'm trying to say that LQ is contained in LP whenever Q is bigger than P. And in effect, L infinity is the smallest space. It's inside of every other LP space. When your space is a finite measure space, which we're dealing with probability spaces, so that's true. Our argument needs to use L infinity on the one hand, but also L2 on the other hand, as we'll see. And it's an interesting juxtaposition of these two things, right? The whole argument can't be done at the level of L2, but you only need L infinity somewhat weakly, and you can pass to L2 in a nice way. We'll start off with something easy. Define our invariant subspace, our T invariant subspace, as just any function in L2 such that it's invariant under T, meaning if I look at G T of X equals G of X almost everywhere. I'm picking L2 because ergodicity is actually equivalent to a statement about L2. It says that the eigenvalue of T as an operator on L2, right? So this operation where I precompose a function with T gives an action on L2 on the space of functions. In particular, it takes, because of the measure of preserving, it takes an L2 function to an L2 function. But the ergodicity assumption says that it has a simple eigenvalue at 1, meaning that the only functions which are invariant are constants. And we'll use that in a moment. I start with these invariant functions. Great. We can see that they actually are invariant under the averages as well. So I know that G of T is equal to G, but then I take G and I apply T to it again. That's also equal to G because it's equal to G of T, and so on. And so that we actually get that if I look at any average applied to a function, to an T invariant function, it gives me the same function back. Now that means that if we look at the limit as n goes to infinity of an of G, well, that's always equal to G. So as I take the limit to infinity, it's also equal to G. Now, what I just say, I said since T is ergodic, the only T invariant functions are a constant almost everywhere. So in particular, the invariant functions are equal to constants. And since our probability space is a probability space, that means it's equal to the integral of that constant over the whole space. So these time averages are the actual space average. Let's consider a case that's pretty different from that. That's the case of cocycles. And now instead of before we had the invariant ones, we said G composed with T is equal to G. almost everywhere. Well, that's basically the same as, that is the same as saying G composed with T minus G is 0 mu almost everywhere, right? But now we're going to actually just look at any function G and then subtract off what happens when we apply T to it. This is a cocycle because I've taken a difference in the orbits. Well, this doesn't quite work if I just consider things in L2 at first. I'm going to assume that my function G is in infinity. Because now, if I look at an average applied to G minus G composed with T, then telescoping gives me that I actually just have two terms appearing in that sum. I have G composed with T and G composed with T to the n plus 1. It's a Q calculation to do. And since G is in L infinity, G composed with T is in L infinity, assume both are bounded by 1. Then this average here is bounded by n inverse times something of norm 1 minus something else of norm 1. And that means they're combined, they're at most norm 2. Their difference is at most 2, right? So this in particular is at most twice the L infinity norm of G divided by n. Since I assume that G was bounded almost everywhere, this tends to 0 almost everywhere. Okay, that's, I mean, this is also actually what we expect. Since T is measure reserving, we know that, let's see, T inverse of E, a measurable set, mu of that is equal to mu of E. The functional version of this is just that the integral of G is equal to the integral of G composed with T. So the integral of G minus G composed with T is 0. And we have that this goes to that integral, the space average is 0, and this time averages tend to 0 as n tends to infinity. Now, I've just done what seemed like two cooked up examples. The cool thing is, these two examples, everything else can be decomposed into a combination of these two. In particular, this is saying that the invariant functions and the cocycles are orthogonal to each other. And then taking the sum of their closures is all of L2. Right, clearly the invariant functions are a closed set inside L2 because it's a subset of L2. It's the showing the cocycles that we have to take the closure of. So what are we going to do now? We're going to show that I is perpendicular to C. And the way we do that is by, all we have to, we want to say it's to the closure. The only way we do that is we just take some G in L2 such that G is perpendicular to F for all F in C. Now, this actually isn't a hard thing to do. No, sorry, we show that this sort of thing implies G is invariant. That's going to give us the orthogonality. the direct sum decomposition. I've been very imprecise about this. What do I want to do? Let's say this better. I want to take any function, f, and I'm going to write it into f is an invariant part and f is a cocycle part, where fi is perpendicular to fc. That's not exactly true. What I can do is I can get any approximation to this, as fine approximation as I want, because this is going to be coming from this cocycles, where I'm assuming an additional fact that this is an L infinity. But that's fine. It turns out that if I have any invariant parts, any invariant function, it is orthogonal to the cocycles. And now we just need to show that if I have anything that is orthogonal to the cocycles, it must be an invariant function. Because that allows me to write this sum uniquely. Great. Assume your function is orthogonal to the closure of the cocycles. That means it's actually orthogonal to the cocycle formed by itself, which is just another way of writing this. And assume this is the inner product on for L2, right? This thing by definition, the integral of g times g minus g composed with t d mu on x. Well, we just move things over. We know that we know that this factors out, but you just use distributivity, right? This is g interproducted with itself, and then g interproducted with g translated by t, or acted on by t. And so that we get that the inner product of these two things have to be the same, since their difference was 0. Nothing deep there. But now here's where we use that t is ergodic. It means it's a measure preserving operator. It gives a unitary operator on L2, so that we can move t around a bit, right? The measure preserving tells us that if I look at g interproducted with itself, I can do g composed with t interproducted with itself. And those two things have to be the same. It's the same manifestation of g is equal to g composed with t, but now on L2. And I knew from before that is equal to this. So that means I have this difference, which is 0. And you add the two equations together, you end up getting that the cocycle of g interproducted with itself is 0. So I have a function which, when interproducted with itself, is 0, means that that function is 0 almost everywhere. And that just means it's a cocycle. Sorry, it means it's an invariant function. This cocycle is an invariant function because g equals g composed with t almost everywhere. So the final step now is actually just, we've shown that the limits converge. And it's just to show that that converges to the space average. This follows from the ergodicity because the space of invariants, of invariant functions, t invariant functions, were just constants since t is ergodic. And so that means that these things, that sequence has to go to some constant function, and that constant function turns out to be the probability space. Oh, sorry, the average, the space average, over that probability space. So are there any questions? I know it's getting a bit late and tiresome, so that may not have been the clearest description. Okay. Let's move forward then to prove the ergodic Hardy Littlewood maximal theorem. The last thing was really just tools from ergodic theory, understanding invariant functions and cocycles, and what it means to be ergodic. This next part is really understanding what it means to be measure preserving. It's not much more beyond that. With that in mind, what is it we want to prove? Well, we want to prove the ergodic Hardy Littlewood maximal theorem, which says if I take this maximal function, which was the supremum over n of these ergodic averages, so ANF of x was, remember, an inverse f of t to the n x. And we want to take the absolute value. Then we want to show this level set inequality, where now this is much like the one we proved before, but our measure has been replaced by mu, or our Lebesgue measure from before has been replaced by mu. And we're not really recording what that constant is. It comes from the discrete, the constant you get in the discrete inequality, as we'll see shortly. Great. So we're proving this, assuming that we get to take the discrete inequality for granted. The real question here is, how do you bring in the discrete one? How do you get a discrete maximal function into play? How do you get some discrete averages into play? That's brilliantly done by the transfer function. I take each point x. I fix a point in my probability space, x, and you define the transfer function, which is now a two-parameter function or two-variable function in terms of my point in the probability space and an integer n, where the integer n is going to record how far along in the orbit of x I've gone, the orbit along iterates by t. And we're actually going to make this compactly supported by taking some big K, not defined yet. And we just define our transfer function as I've written here. Oops. I'm hitting the eraser. There we go. For these, for times up from 1 to k, we just define our transfer function to be the value at that point in the orbit. And then for bigger times, it'll be 0, or when n is negative. Okay. This function now is a function of x cross z. It's defined for almost everywhere x and for all integers n. We can introduce a transferred maximal function where you just take the supremum of these new averages. That should be x of n. That should also be x. N. But I'm going to truncate the maximal function like I did before. This, you can also, as long as we obtain a bound that doesn't depend on j in the end, then we're golden. We just apply a monotone convergence argument and we take the supremum over all natural numbers. Our maximal function, since it's been truncated, also has finite support. It's supported in x in the first variable, of course, and then now j plus k in the integer variable, the second variable. And the critical observation here is really how the L1 norm for each layer of the transfer function compares to the L1 norm of the function on the probability space we started with. Right? And this just follows from the measure preserving property. I have in particular, if I look at F, so again, F is defined on X cross C. If I look at it as I fix my integer n, and I look at it as just a function on X now, that has the same L1 norm as my original function F. So Fubini's theorem tells us that, well, when I look at the transfer function on X cross K, or the integers from 1 to K, with the measure that is mu on X as before, but now counting measure on the integers from 1 to K, since each one of those was the same, this is K times the L1 norm of F. Now let's look at the averages in the maximal function. Well, the averages were just defined as this. There should be a plus n there. Remember my f of xn, m, sorry, is f of t m the x. And so when I hit it with t to the n, I just shift, I go further along in the orbit. And then I average over that stretch of the orbit. So the picture to keep in mind now, I think, is consider, I've got, that's a very bad picture. Let's go back. I've got right, each sort of point of lack of continuity is a new time. At time 0, I just have f of x. Well, then I have f of t of x here, and then f of t squared of x, and so on. This average says, all right, I can do it for f of x 0. I will take the average that goes, let's say it's 4 steps. It takes this value, this value, this value, this value, there. And then at time 1, it goes to 2 now, and it goes this value, this value, this value, that value. And then at time 2, it keeps moving along. We see that if our orbit is really long, then there's a lot of overlap between the sort of initial few points and the latter few points that the tail goes out into. All of that is a way to say that I can compare my ergodic maximal function at certain points inside the orbit with the maximal function, the discrete maximal function for my transferred function. And I can do so sort of in this regime, this yellow regime. And again, since t was measure preserving, I get an equality of these level sets, because each set is just a mu measurable set. And I get that in some slightly smaller range. Basically, I have to ignore the first few values so that I can get the parts that overlap all the way. And now our transfer function, as a function in just the integer variable, satisfies the discrete Hardy Littlewood maximal inequality. Oh, so there's some constant, sorry. C here coming from the constant from the discrete Hardy Littlewood maximal inequality. Which we get to apply to each layer in terms of x. So each point x that was starting in that was defining my orbit. I know that we have this bound for the transfer maximal function. And so integrating over the whole, integrating over all the possible points, we end up getting this bound. Where it's a hybrid bound on x cross z. And there should be a constant of c here as well. All right, as in our in the picture I was drawing, right, there's a sort of head of a few values in the orbit that we like before we get to where we really want to go. And there are all these tail values of the orbit that were sticking out. If you ignore those two ends, so you have just that bulk contribution in the middle, it all overlaps. And assuming that n is basically the same size as that, then you really have the same, you're measuring the same amount of the orbit. Now, to make that precise, another C here, you find that, look, if I just take x and I restrict it to this, sorry, not x, if I take x cross z and I restrict it to x cross the first k minus j terms, then I can bound this by the one with the k at the end. But we already saw the measure preserving property meant that this was k times the L1 norm of f. Right, so this is equal to this. And similarly, the left-hand side of this is equal to just k minus j, because of that part, times the level set of the ergodic maximal function. Now to deduce that this level set is bounded, all you do is you move the k minus j over, you take k to infinity, and that gives you the weak type 1-1 inequality for the ergodic maximal function, assuming, again, the weak 1-1 inequality for the discrete version. And again, now that bound didn't depend at all on j. It's just a constant times alpha inverse. So you can just take j to infinity in order to conclude it. The reason we can't let j go to infinity in the first part is we really have to consider these orbits, finite parts of these orbits, but an arbitrarily large part of it. Great, so that completes the proof of Birkhoff's pointwise ergodic theorem, where the homework is to prove that discrete Hardy Littlewood maximal theorem. Are there any questions? Right, well, I'll stop there today, and next week we'll pick it up with more on maximal functions, averages over hypersurfaces, and the spherical maximal function. Thank you.